Standard deviation. Wow, what a formula. Yeesh. Let's break it down one step at a time. As with all mathematics, we follow the order of operations. That means we start, when there's multiple grouping symbols, we start from the inside and work our way out. So, the first thing that happens in this formula is that for every data value, we find its distance from the mean. This is the deviation. Now, as we saw in the slideshow, the deviations are negative if the data value is below the mean and positive if it's above the mean. But they always balance out perfectly to zero. That's kind of the idea of, the mean acting as a center of gravity or as a balancing point, that the total amount of influence on one side is completely and perfectly balanced by the amount of influence on the other side. So if we were to just add up the deviations in every data set, we would always get zero for every data set in the history of the world, ever. That's not very helpful. So we need something that's going to help preserve that idea that some of the data values are further away than others, that something that is 5 spaces above the mean is not as influential as something that's 20 spaces above the mean. So we need something to measure that, but we also need to recognize that a value that's 5 below the mean has the exact same amount of influence, just in the opposite direction, as a data value that's 5 above the mean. If they're the same distance to each side, they have to have the same influence. So we need something that's going to maintain the amount of influence it has without canceling each other out. And a really good way to do that is to square the deviations. The idea is that if I square the 5, if there's a data value that is 5 below the mean, and a data value that's 5 above the mean, well, negative 5 squared is 25, and positive 5 squared is also 25. So we're maintaining that those two values have the same amount of influence, but in this way they're no longer going to cancel each other out. In very much the same way, we're also preserving the extent of the influence. A value that is 5 above the mean, squaring that becomes 25. A value that's 20 above the mean, squaring that becomes 400. So the squared deviation is 400 versus the squared deviation of 25. We can see that that value that's 20 spaces above the mean is still exerting a much greater influence than the one that is only 5 spaces above the mean. So squaring allows for the removal of that cancellation of left and right, but at the same time preserves the fact that we're now just looking at distance. We don't really care to which side, just distance in general. So it has the effect of removing the negatives and still preserving the relative influence that each value has as far as the size of its deviation. So now it makes sense to add them up. So that's the next step. We're going to sum the squared deviations. Now you might recognize a familiar element to this. Adding up a bunch of things, and then the next step is to divide it by, well, if we ignore that minus 1 in the denominator for a quick moment, if we're adding up a bunch of stuff and then dividing it by the number of things that we added, that's the mean. But it's not the mean of the data values, it's the mean of the squared deviations. Now, the square root's going to come into play to kind of balance that out and return everything to its regular size. So that 25 will get square rooted and go back to being a 5. But the thing that was 5 below the mean, when that got squared, it went to 25, and the square root will drop it back to a positive 5. So for all intents and purposes, the point of the squaring, and then later the square root, is to basically eliminate the left or right, the below the mean or above the mean, and to just keep it as, hey, let's just look at their distances. Now, the -1 is an interesting thing. That has to do with something called degrees of freedom. That is a concept that is beyond the scope of this class. It does show up a lot in a number of things that you're doing in statistics. It has to do with the idea that if you were creating a data set, you only have so much freedom in the values you're choosing. Like, say, I was inventing a problem. I wanted to create a data set that had a particular mean. Well, if I know how many things are in the data set, and I know what I want the mean to be, then that kind of dictates to me what the sum of the data values has to be. So I can kind of choose at random what values I want, but eventually I'm going to get to a point where I'm kind of locked in. So degrees of freedom has to do with that. How many of those values can be freely chosen before the last one is automatically determined by the nature of the problem. Again, it's kind of a complicated thing. It's something that the people who developed this stuff need to be concerned about. And it's something that you need to be aware of as a concept, but not that you need to know the background of. But the best thing I can tell you for now is just because that's part of the formula. So, we take the sum of the squared deviations and we divide it by, not the sample size, like in a regular mean, but by 1 less than it. And lastly, we put a radical over the whole thing. Now, as I said, that radical is to kind of correct the amplification that the square did. Remember I said if something's 5 above the mean, we square that deviation, it becomes 25. So the square root is to kind of return us to the original scale. Now, between the division and the square root, chances are this is going to be a disgusting decimal. So we will follow the typical rounding rule that we use for the mean, and that is however many decimal places the data set is measured to, we will round to 1 more decimal place. So if we're dealing with a data set of whole numbers, then the standard deviation and the mean would both be rounded to 1 decimal place. If we're dealing with a sample where the data is measured to 3 decimal places, then the mean and standard deviation will get rounded to 4 decimal places. Always 1 more decimal place than that to which the data itself is measured. But this is essentially what the standard deviation is doing. It's taking the distance from the mean, squaring and later on square rooting to remove the left or right. But essentially what it's doing is it's finding the average distance from the mean. And that really is the best interpretation of the standard deviation. It is, for all intents and purposes, it is essentially the average distance that a data value from the data set is from the mean. That is essentially what it is. Now, okay, not exactly, because that -1 kind of screws stuff up a little bit. And we're not squaring and then immediately square rooting. We're squaring, adding them up, and then square rooting. So, there's a little bit of mathematical kind of hairiness in there. But for all intents and purposes, that's what the standard deviation is. It's telling you the average distance that a data value is from the mean in your data set.